This is the screencast for section 4.3, example 7. We're going to learn the second derivative test for local extrema. So you can use the second derivative to tell if the original function has an extrema. So for example, if the first derivative equals 0 and the second derivative is negative, so in other words, if the original function is concave down, then you have a local max in the original function. And you can kind of see I drew, like, it would have a horizontal tangent, that's f prime of c equals 0, so the slope there is 0, and it's concave down. Number 2, the second option here is if we have f prime of c equaling 0, and then the second derivative is greater than 0, so the original function is concave up, a very similar situation, and then you have a local min in f at x equals c. So we'll use that second derivative test here in the example 7. Find the local extreme values of f of x equals this. So first I have to find the first derivative and see where it equals 0. And the zeros of f prime are positive and negative 2, so f will have horizontal tangents at positive and negative 2. So now I need to test the second derivative. So I found that the second derivative was 6x. So I plugged in 2, so 6 times 2 is 12, which is greater than 0. So since f prime of 2 is 0 and f double prime of 2 is greater than 0, the function would be concave up, and therefore f has a local min at that horizontal tangent at x equals 2. Now f double prime of negative 2 is less than 0, so therefore f would be concave down, and there's that horizontal tangent there, so f has a local max at x equals negative 2. The now try problem number 35 asks us to again use a second derivative test to find the local extrema for the function. So I found the first derivative and its zeros, and I see that the original function will have horizontal tangents at 0 and 2 because the first derivative is 0 at x equals 0 and negative 2. So now I need to find the second derivative and plug in y prime of 0, which is going to be greater than 0, so therefore f will be concave up, and therefore at that horizontal tangent f will have a local min at x equals 0. And now I'll plug in negative 2 to the second derivative, and I get that the second derivative then would be negative, so the original graph would be concave down at that horizontal tangent, creating a maximum at x equals negative 2. And of course you could graph the original function to make sure that there was a minimum at x equals 0 and a maximum at x equals negative 2.